Good morning, one and all again. Welcome back in Sanjeevanee Mahavidyalaya Chapoli. This lecture is for B.Sc first year physics students, paper number 1, semester number 1, topic mechanics. Paper name of the paper is mechanics, properties of matter, and unit is viscosity. In last lecture, number 1, we have seen about what are the fluids more viscous as compared to other fluids. And we also see about the concept of viscosity. Syrup is more viscous compared to water. We have also seen the mathematical expression of viscosity, and this eta stands for coefficient of viscosity. We have already seen. We have also seen this concept that an important is that viscosity simply explains the fluid's flow resistance. Up to this we have arrived in last lecture. Now we shall see the another. Now we turn to lecture number 2 about viscosity. The thing is that a very important question, most of the people they didn't ask. Some students, some people may ask, why even measure viscosity? Concept of viscosity clear. Then question arises, why we utilize or why there is a need of measurement of viscosity? Surely there is a need of measurement of viscosity, but why it is? Some students, some people may ask. The main reason behind this is being that the viscosity data on the material gives manufacturers a chance to predict how the material will react and behave when consumers interact with it. The most simplistic formula for measuring the viscosity is equal to shear stress upon shear rate. Shearing stress upon shearing rate. Then, what about critical velocity? Critical velocity of a fluid. Say, whenever fluid flows, water flows, glycerin flows, or kerosene flows, oil flows, whatever may be the fluid, whenever it flows, then it will acquire a greatest velocity with which fluid can flow through a given conduit without become turbulent. You may ask again, what is turbulent flow? That turbulent flow and streamline flow, the concept we are discussing in next slide. So at present you remember the greatest velocity with which a fluid can flow through a given conduit without becoming turbulent. It means before reaching to the turbulent stage, what fluid acquires maximum velocity, that is said to be critical velocity of the fluid. Got it? This can utilize for kerosene because its viscosity is different than the viscosity of other fluids. This can is utilized for measuring the oil as its viscosity is more. Already we have seen in lecture number 1. Now very interesting picture you see. What is this? What is this? This liquid is what? This liquid, what it shows? Here drops are forming. It is not easily gets poured. It doesn't get easily poured. It means it is more denser. we say. I mean, instead of saying more denser, better to say it is a viscous liquid. It shows the nature of viscosity of a liquid. From this figure, you will come to know that it is not easily going to flow. There is more opposition to the flow of this liquid with adjacent layers. Now, let's turn towards the introductory part. Viscosity is a quantitative measure of fluid's resistance to flow. Viscosity is nothing but quantitative measure of fluid's resistance to flow. Then what are the types of viscosities? There are different types of viscosities. Dynamic, and another one is kinematic viscosity. So among these two types, what is dynamic? First we shall see. Dynamic viscosity is also said to be absolute viscosity. What is dynamic viscosity? Dynamic viscosity denoted by eta of a fluid is a measure of the resistance it offers to the relative shearing motion. This point you remember, relative resistance it offers to relative shearing motion. This is nothing but the measure of a fluid, and it is said to be its viscosity. Measure of the resistance of a fluid, that is said to be dynamic or absolute viscosity. Now let's turn towards this figure. Here what happens? The flow is flowing. Fluid is flowing. Here arrows shows what? These arrows shows the directions. I mean, fluid is flowing from left to right, you may say. There are infinitely many thin fluid layers. Few layers are shown here practically, but there are infinitely many layers. This is a F is a force applied on this fluid. What is H? What is area? Area is nothing. A is nothing but area of cross section. So this dynamic viscosity or absolute viscosity can be calculated by using this formula. Eta is equal to F upon A into U by H. That is, eta is equal to tau U by H, Newton second meter per square. Then question arises, what is U, what is A, what is H, and what are these? These are the different infinitely many fluid layers in a pipe, you can say. Here U is equal to 0, and here U is maximum. Here velocity of the layers is going to increase from bottom to top. Are you agree? It means lower layer possesses zero velocity. It is considered as what? Very slow layer. And as we go to the upper and upper layers, then speed of the adjacent layers is going to increase. So this is nothing but speed of the layer. So lower layer is considered to be the speed is 0 because it resists, or there is a more opposition to the flow of this layer with the container. H is nothing but what? Width of the container, area of cross section of the container. It is given. Okay, later on you see. It is given here. U is nothing but this U stands for what? Velocity of upper layer, uppermost layer is maximum. Here initial velocity is what? Very less. A stands for area of cross section. H is nothing but width, and there are infinitely many layers. So using this, you can find out the viscosity of the liquid, I mean dynamic viscosity of the liquid. Now let's turn towards another type of viscosity, that is said to be kinematic viscosity. It is defined as the ratio of absolute viscosity to the density of the fluid. Very easy to remember. What is it? It is nothing but the ratio of absolute viscosity, which we have earlier seen in type number 1, to the density of the fluid. Again, question arises, what is meant by density? Density, as its mathematical expression is mass upon density is equal to m by v. The ratio of mass to volume is nothing but density. So such a ratio of absolute viscosity to the density of the fluid is said to be kinematic viscosity in meter square per second, where rho is nothing but density of the fluid. What is this rho? It is a density of the fluid. Density of the fluid. Now, if we think about the viscosity measurements, capillary viscometers are utilized to measure the viscosity of the liquid, viscosity of the fluid. It gives the kinematic viscosity of the fluid, and it is based on Paul's law for study of viscous flow in a pipe. There is a law, say Paul's law. What is that Paul's law? Later on we are going to discuss. So kinematic viscosity of the fluid can be obtained, or can be measured by using this capillary viscometer. Capillary viscometer is used for the measurement of kinematic viscosity. It is based totally on Paul's law for study of viscous flow in a pipe. I will show you this capillary viscometer. Capillary viscometer is a such type of tube shown in picture, as shown in picture. Here solution pulls fluid to start mark, and here stop mark. This is the capillary section, and time is to be set first. Here start mark is shown here, and here stop mark. Once the start mark is there, then we have to start this stopwatch, and whenever the fluid reaches to this position, that is stop mark, here one has to stop the stopwatch. Then we can measure. These levels, and then by using this formula we can obtain the viscosity of the fluid. Here formula is pi r raised to 4 GLT upon 8 LV, or it is equal to constant K T2 minus T1. Then question arises, what is this pi? What is pi is constant? What is R? What is G? What is L? What is T? What is this capital L? All these things. Here V is the kinematic viscosity in meter square per second, and small r is the radius of the capillary, and L is the mean hydrostatic head. Small g is the Earth's acceleration, or acceleration due to gravity in meter per second square, and capital L stands for the length in meter. I mean capillary length in meter, entire length. V is the volume of the fluid. How much volume of the fluid is going to flow through this. Remaining matter we shall see in next lecture. Thank you.